We live in a universe, and in this universe are things. Now, I've already confused all the philosophers in the room, but while the rest of us don't know what we don't know, philosophers don't even know what knowing is, so I doubt they'd be able to keep up with the rest of us anyway. Anyway, the central claim of science is that we can find out about these things by observing them, and that through well-designed experiments, we can make theories about how these things act. Through this observation, we found that these things obey Newton's 3 laws of motion. Except, Newton's 3 laws of motion aren't always true, aren't really laws, aren't strictly about motion, and actually there's only one of them. It's really more like one big definition of a force. So let's talk about how we get there. The core observation Newton had was that when nothing was happening to a thing, nothing was changing about that thing, which is, revolutionary, I know, but this is actually important. It means that to change something about the motion of an object, like speed or direction, then something has to act on that object. A force. Anyway, this paradigm is helpful because it means that when we want to do something to an object, like stop it from moving, we can now talk about exactly how difficult that will be. This particular difficulty has a name. P is called momentum and equals mv, where m is the inertial mass of an object and v is its velocity. You might imagine that if we want to stop an object from moving, we both have to incrementally slow down every bit of its mass, and we have to keep doing that from its current velocity all the way down to 0. I mean, it's kind of obvious. It's easier to stop a baby from falling onto a piano than it is to stop a piano from falling onto a baby. And it's easier for a bullet to stop you than it is for you to stop a bullet. So, what is a force? A force happens when the momentum of an object changes over time, and Newton's law says this mathematically. I hope I don't have to explain to you the F equals over there, but the P up top represents momentum, and the D over dt asks how much does this change at any instant in time. It looks like a fraction, and it's basically a fraction, but don't let the mathematicians hear you say that because they'll actually kill you. I've seen them do it. So anyway, that in itself isn't all that revolutionary. Like I said, it's basically a definition. Way to go, Newton, you invented calculus. I'm sure everyone's gonna love you for that. No, the important thing Newton did was discover that forces exist. Okay, well, obviously the momenta of things change, so forces exist, but Newton showed that they're predictable. That is, given the state of a system, we can figure out exactly what forces that system will experience. Specifically, he showed that the force of gravity is a thing, and here's the formula. So the r squared here in the denominator is basically saying that the further away you get from an object, bigger r, the less powerful gravity is. And the g up top is a factor which determines how strong gravity is overall. The m1 and m2 here, though, are kind of confusing. They're the masses of these two objects that are exerting this force on each other, but they're not the same masses that you use in the momentum formula. This is called gravitational mass, whereas momentum deals with inertial mass. Gravitational mass, which is this, tells you how strong the force of gravity is from an object, and inertial mass tells you how hard it is to change an object's velocity. They really don't have all that much in common if you think about it, but remember the fact that there are multiple kinds of mass because, spoiler alert, it'll be important later. Lucky for us though, it just so happens that these two are exactly equal. And that's that. Congratulations, you can now calculate gravitational force between any two objects. This formula works no matter which direction you're facing, where you are, when you are, how fast you're moving, or how fast you're spinning. It works. In fact, if you know the state of the whole universe and your own gravitational mass, then you can draw an arrow from where you are in the direction of gravity. And you can pretend that you're somewhere else and draw an arrow as if you were there instead. You can do this for every point in space, and this is called a field, or specifically a gravitational force field. And now, knowing what the words mean, the idea of a force field sounds a lot less cool. Well anyway, you can look at where you are in this force field, figure that you're bored of this video and want to go home, and you can ask yourself, how much more arrow do I have left until I get back home? This is a harder question than it sounds because, keep in mind, you don't actually follow the arrows exactly. These arrows only represent how much your momentum changes, not where your momentum will be pointing. Still, you could ask, if I end up taking this given path, how much will I follow the arrows? Luckily, we have a math for precisely this question, and it's called the dot product. You get it by multiplying up the corresponding components of your two vectors, and then adding it all up. So, if you dot f with dr, the direction of your path at a given point, you get how much you're following the arrows at that given point. And for all you people above the age of 6, that's a measure of the amount that the direction of the path lines up with the direction of the force. If you add all this up across your path, you get the total amount that you followed the arrows. That is, the total amount that the force contributed to your motion, the work done by the force. Now, calculating this can be difficult. You get an ugly looking thing called a line integral. This is because both your f and your r change depending on where you are, so you have to recalculate the dot product for literally every single position on your path. We do this by splitting the path up into very small parts, dr is going to be our small change in path, and then dot each of these vectors with f at that given point. And then we add it all up, which is what this symbol represents. So what do smart people call how much you follow the arrows? They call it the change in energy of the object. So if you start your path with 0 kinetic energy and you happen to move along this path, then you will end up with this much kinetic energy. Lucky for us, integrals for conservative vector fields are path independent, proof, and lucky for us the gravitational force field is conservative, except for sometimes, so lucky for us, we don't have to calculate hard integrals whenever we want to investigate a new path. We just have to do it once between the endpoints of that path, and now we know the work for every path in between those two endpoints. So let's try that. Gravity is a radial force, meaning it always points directly in or out. So if we have two endpoints, one r1 away and the other r2 away from a gravitational source, then we can split the path into one section with a constant r1 difference, and another which goes straight from r1 to r2 directly away from the mass, that is, directly aligning with the direction of the force. For the first section, dr and f are perpendicular, so the dot product and work are therefore 0. For the second, dr and f align, so the dot product is just the magnitude of f times dr. So to actually calculate this integral, all we have to do is define endpoints for this second section, that'll be r1 and r2, and follow some rules of integration. And even though I said this video was from square one, I really don't want to explain how to do integrals. So here's the formula, here's the derivation for the formula, and here's the simple version. None of the rest of this depends on r, so you can take it out. Now look at the exponent of r, add 1, divide by it, plug in the first and last values of r, take the difference, and there you go. That's the change in kinetic energy due to gravitational force for a path starting r1 away from gravitational mass and ending r2 away from it. But we can make this a bit easier. First, physicists like it when things don't change. So what we do is, whenever the kinetic energy of something changes, we just change some other kind of energy in the opposite way, so the total amount of energy stays the same. Unfortunately, there's only one kind of energy, kinetic energy, and we can't change kinetic energy in order to offset a change in kinetic energy. That doesn't make any sense. Sometimes we really can't change kinetic energy, and we call that stuff heat energy, so we usually set it apart. Since we can't intentionally change heat energy at all, we really can't change it in order to offset a change in kinetic energy. This means that if we really want to make total energy a constant value, we simply have to make up a new kind of energy. And all of the other kinds of energy you've heard about, solar, nuclear, chemical, potential, they're all made up. They're simply not real. For example, we say potential energy is the kinetic energy an object could access, but it doesn't really exist, we just say it does so that our math works out easier. Potential energy is defined to be total energy, which doesn't change because we say so, minus kinetic energy minus thermal energy. Therefore, whenever kinetic energy changes and doesn't go directly into thermal, potential has to change because we say so. The only reason that asserting this so proudly actually works out for us is because we can explain where all the kinetic energy comes from. We have excuses for adding and subtracting potential energy, and we call these excuses forces. Energy is conserved basically translates to we know all the forces, and let me tell you, that makes things a whole lot easier. If you did your math right but your energy doesn't add up, it's because you forgot a force, simple as that. So going back to our definitions, if this is our change in kinetic energy, and potential has to change opposite to that, then this is our potential energy change, and actually, I like it better when we take the derivative. Don't get what just happened there? I divided by dr on both sides, and instead of summing up a lot to get a large change in potential energy, we're now not summing, and instead looking at a small change in potential energy. This should remind you of our original definition of a force just a bit. Using this original definition, we can also get an easy way to look at kinetic energy. Here's our kinetic energy formula, now substitute Newton's law. Rearranging, we get this. And dr over dt is just how fast an object's position changes in time, the velocity. Now, dp equals dmv, and since we're assuming inertial mass is constant, a small change in mass times velocity is actually just a small change in velocity magnified by the total mass. We now have the integral of mv dv, and we just do our regular old integration. M doesn't depend on v, add 1 to the power of v, and divide by it. Delta ke equals 1/2 mv², evaluated at v2 and v1. And here's the other thing about energy. If we use these formulas, we only ever get to talk about a change of energy. We never give the amount of actual energy in the system a number in and of itself. Unless we want to, in which case we have to set a 0 point, which is a state under which the system has 0 energy. Because kinetic energy is actually real, then there is a state under which a 0 point actually makes sense. At 0 velocity, we say the state has 0 energy. We can now calculate absolute kinetic energy as a function of velocity. All we have to do is set v1 equals 0, and now we have a formula for absolute kinetic energy. It's exactly this process we'll do again in order to get E equals mc² later, but we'll get there. For something like potential energy, our process is more complicated. We have our formula for delta KE due to gravity, but by inverting it, we get delta PE due to gravity, which is still pretty ugly. We could make it prettier by setting a 0 point, but since potential energy isn't real, there's no right place to put that 0 point. It's all okay as long as we push through the math. For most forces, it's mathematically convenient to set the 0 potential energy point at r equals infinity, which makes the second term here 0. Note that this means gravitational potential energy is always negative. That's fine. This is fine. Now, I know I've spent a long time on energy and not directly building to E equals mc², but it's really important to understand what energy is in order to understand what that formula means. In fact, I think most physicists really get caught up in the formula's math and applications without ever acknowledging what the formula itself actually says. People point to E equals mc² and say, wow, mass is energy, or this means we can transmit mass into energy. But it really doesn't mean that. For example, here's another formula involving energy. This one's for gravitational potential energy near Earth's surface. U equals mgh, where h is height. Using the same logic, we might shout, wow, height is potential energy, or this means we can transmit height into potential energy. And there's a little truth in that. Because there is a correspondence between height and U, changing one will change the other, sure. But it's not like they're the same type of substance. Height is a measure of distance in space, whereas potential energy is the negative amount of following the arrows an object could do if it were allowed to take an arbitrary path to some arbitrary 0 point arbitrarily far away. We don't express them in the same units, and they're not even the same category of concept. They just happen to align, like gravitational and inertial mass. The same will go for E equals mc². Changing mass will mean changing energy. There's a correspondence, sure. But relativistic inertial mass, which is the type of mass described here, it's a resistance to a change in motion, whereas the type of energy described here, it's a bit of a mix of kinetic and potential energy. Arrow following and resistance to motion, again, they're just not even the same category of concept. They just happen to correspond. So where does this leave us? Let's recap. We live in a universe, and in this universe are things which behave predictably as a result of forces. Gravity is an example of such a force. When a force contributes to the motion of an object, it changes that object's kinetic energy. And in order to check our work and make total energy constant, we make up new types of energy, like potential energy. We defined or derived formulas for momentum, kinetic, and potential energy, but we saw that just because it said that E equals mc², that doesn't mean energy and mass are the same type of substance. In the next part, we'll discuss types of forces other than gravity, show that the speed of light is constant, and get a simple introduction to special relativity. I appreciate constructive criticism, and I'll see you strangers later.